Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we talk about all things Gen Chem related. On this video, we'll be covering trends in bond energies and bond lengths and using those bond energies to predict the overall enthalpy associated with the chemical reaction. Let's get started. So if you recall in previous videos, we talked about the overall trend that existed between bond lengths when we were looking at things like double bonds and single bonds and triple bonds, and also the amount of energy associated with them. Well, in this video, we're going to be delving a little bit deeper in that. And at the end, we're going to learn how to use the bond energies to figure out how much enthalpy would be associated with a particular reaction. This is going to be reliant on us being able to draw Lewis structures and then look up the associated energies. Okay, so let's just revisit bond lengths. Now remember, with the bond lengths, our triple bonds will end up being shorter than your double bonds, which would end up being shorter than your single bonds. So single bonds are going to be the longest. We can also tie in the bond length in with the overall atomic radius that we know that exists with these atoms. So remember, as we go down the periodic table, the atomic radius gets bigger and bigger, right? The number of electrons that are present. So the length between the bonds that would occur will get bigger and bigger and bigger as we go down the periodic table. So you can see that taking place on this slide. We could also see that depending on the type of sharing that's there, that will also impact the overall length. And so if you have like a triple bond compared to a double bond or a single bond here, you can see again that length gets shorter and shorter as you add more and more bonds. So those trends do coincide with what we've seen before, okay? And so in general, as bonds get longer, they're going to also get weaker. Now that idea, the fact that they're getting weaker as they're getting longer, ties in directly to the amount of energy that would be needed to either create one of these bonds or ultimately come in and break a bond. Okay, and so remember, chemical reactions, when we're creating something new, what that process really involves is making and breaking bonds. So we're either creating new bonds or breaking bonds. And there's energy that's required for each of those processes. Now, the enthalpy of the reaction can be estimated by comparing the amount it costs to break old bonds versus what's gained by creating new bonds, okay? And so remember, what you want to think of when we're breaking bonds, that means we got to punch in energy. We got to add some energy. And as we create new bonds, that's lowering the potential energy of these atoms and this overall molecule. And so we're going to be releasing energy, okay? So just keep that in mind. Breaking bonds, we're adding them. When we're making bonds, we're releasing energy, okay? And the overall energy it takes to break 1 mole of a bond in a compound is what we call the bond energy, okay? And so there are, again, trends that exist here. The more electrons the 2 atoms share, the stronger that bond would be. So if I have a triple bond, the amount of energy that's needed to come in and break it up or create it would be much higher than what it would be if it's a single bond. Now, remember, we talked about the fact that although it's a triple bond or a double bond, the energy associated with it is not automatically translated to being exactly twice as much or exactly 3 times as much, even though it is still considerably more. All right, and so again, the shorter the covalent bond, the stronger the bond would be, and ultimately the more energy that would be needed to break or make it. Okay, and so we can use the bond energies to actually estimate what the enthalpy of a reaction would be. And so we can look up the average bond energies that are found or associated with different bonds that are present. Remember, the breaking bond process is considered to be endothermic, meaning that we're putting energy in. We got to go in there and break that up. So we got to spend some money. So it's going to be that positive value. For creating bonds, that process is going to be an exothermic reaction. So we're going to be releasing energy. Now, to predict or estimate the enthalpy of it, we would take the sum of the bonds that have been broken and the sum of the bonds that have been made to represent the enthalpy of the reaction. Bearing in mind that anything that's being broken, we give a positive value because it's an endothermic process, and anything that's being made gets a negative value. Okay, so keep that equation in mind. All right, so if we look at this example here, where we have CH4 reacting with Cl2 to produce CH3Cl plus HCl, we can see where the bond breaking and making occurred. So this is really useful to be able to draw your Lewis structures. Remember, this problem could have been given to you as CH4 plus Cl2 creates CH3Cl plus HCl. And if it is given into you in that manner, the first thing you're going to want to make sure you do is actually write the Lewis structure. Why? The Lewis structure shows me the bonds that are being broken or made. And so you can see that here. So if we compare my reactant side to my product side, I can see where there's a difference. I can see that this carbon to hydrogen bond is now being broken. And this Cl to Cl bond is being broken. And what's being made is this C to Cl bond, as well as this H to Cl bond. Okay? We would then look up on our chart to figure out, well, how much did I have to spend to break it and how much is being released to make it? All right, so if we look on the chart, the C to H bond, the C to H bond would end up being 414. And so we would say positive 414 is needed to break it, plus for the Cl to Cl bond, we would say positive 243. So that's my bonds broken, plus my bonds that are being made. So that's the C to Cl bond. And so we find that, which is, I believe that's at the bottom. I can't see. I think that C to Cl is 339. So negative 339. And again, we say negative because it is being made. It's exothermic, plus the H to Cl bond, which is 431. And we'd say negative 431. And so then when we go to add all that up, okay, we take 414 plus 243 plus the sum of the bonds that are being made, so negative 339 plus negative 431. And that gives us a total of negative 113 kilojoules for this reaction. Okay. So again, take into account what bonds are being broken, what bonds are being made, and then you add those up to get your overall value of negative 113. Okay, good. All right. And so again, what's happening here, we're breaking those bonds. And so there's that change in enthalpy that's occurring. And then we've created some new bonds, and overall we're releasing more energy. So this overall process ends up being an exothermic one. All right, so let's try one more. And so here we have H2 plus O2 creates H2O2 or hydrogen peroxide. Again, here you have to draw the Lewis structures. So if this would have been written as H2 plus O2 plus H2O2 or HOOH, you want to make sure that you first draw your Lewis structures. You then look at what's being broken and what's being made. And so on my reactant side, I see my H to H is being broken. And I also have to, at first glance, you may say, oh, well, only one of these bonds is being broken. But in fact, when you're dealing with this, you need to come in and actually completely break the entire thing. Because remember, it's not exactly equal. One double bond is not equal to twice as many single bonds. So we got to break the entire thing first and then remake the single bond. Okay, so all those are being made. All right, and so then we look at, well, what's it going to cost me? So for my hydrogen to hydrogen, that's going to be 436 positive plus my oxygen double bond, which is 498. Okay, so that's what's being made, or excuse me, that's what's being broken, plus what's being made. And so I see I have the hydrogen to oxygen bond, which is 464, so that'd be negative 464, but I have two of those, so I want to make sure I times that by 2. Okay. Plus, give me some more space here. All right, so we have negative 464 times 2 to represent those two O to H bonds, plus my oxygen single bond, which is 142. And we would write it as negative 142. Okay, and then we add that all up. So we'd have 436 plus 498 plus. Now I'm going to do negative 464 times 2 and minus that 142. Close my parentheses. And we end up with negative 136 kilojoules for this. And so again, this process would also end up being an exothermic overall reaction. I hope this video helped you guys understand trends in bond length and bond energy and how to calculate the enthalpy for a reaction based off of the bond energies. Make sure you guys like, comment, and subscribe, and let me know what other content you'd like to see. I'll see you guys in future videos. Have a great day. Bye-bye.